Welcome, students. I am Aurora, the artificial intelligence system on Spacegate Station. In this episode, you will be reviewing both the concepts and mathematical formulas related to density. Please stand by for transfer to Spacegate Station.
Hey, Specialist Barber. Enjoying the view?
You know, I've been stationed here on Spacegate for a long time, and still, that view never gets old. Where are you headed anyway?
Oh, I promised Professor Schnaus that I would help her with her lesson today. She's transmitting to Earth and discussing density and its implications on science.
Processing. To be dense is a colloquial term that relates to an individual that is slow to learn or understand and lacks intellectual acuity. Captain Codwell, the use of such a derogatory term is both negative and disrespectful, and a violation of NASA's policy on appropriate crew communication behavior.
It's about time this happened to somebody else.
No, Aurora, I wasn't referring to dense as it relates to an individual. I was referring to density as a scientific concept.
Processing. Density relates to the scientific concept of how much space an object or substance takes up in relation to the amount of matter in that object or substance.
That's correct, Aurora. She's going to be reviewing density with her students today in NASA's Spacegate educational program.
You know, that sounds very interesting, and I can't wait to see the recording of the video transmission when it's complete. You know, the concept of density is really important for students to understand. I just hope your students are all ears.
Processing. Specialist Barber, I am confused. Why would we restrict instruction of this important subject to children that are born with more than 2 ears?
No, Aurora, I did not mean the lesson is for children with more than 2 ears. I was just using another idiom. It just meant that I hope that the students are eager to listen to what Professor Schnaus has to say about density.
How interesting. I will save this idiom for future use.
It never fails.
You know you do this yourself. Well, I don't want to be late for the transmission, so I'll see you two later.
Peace and quiet again.
You know, Specialist Barber, I am still here.
Yes, Aurora, I know you're still here. You're always here. You're my one constant on the space station.
You are welcome, Specialist Barber. I find your constant presence comforting as well.
Aww.
Aurora, are we ready for my lesson transmission?
Yes, Professor Schnaus.
Perfect.
Hi, Professor Schnaus. I hope I'm not late to help you with your training today.
Not at all. Aurora, we can begin transmitting the lesson now.
Video transmission and recording has been initiated.
Welcome, students, to Spacegate Station. My name is Professor Schnaus, and I'm in charge of planetary geology for Spacegate Station. And this is Captain Caldwell. He's our military IT specialist, and he's here to help us with our lesson today.
Hi, kids. What are we going to be learning about today?
Today, we're going to be learning all about density. Right, Aurora?
Yes, Professor Schnaus. Density is known for being an extraordinarily hard concept for students and teachers.
That's correct, Aurora, and that's why we're doing the lesson today.
But why is density such a difficult concept for students to learn and teachers to teach?
Well, one reason is that, unlike an object's weight, it's hard to have a direct perceptual understanding of density.
You are correct, Professor Schnaus. When humans hold 2 objects in their hand, they can normally judge whether one object is heavier than the other or whether they weigh about the same. However, when they compare the weights of 2 objects, they can only determine their relative densities if they are roughly the same size.
Correct, Aurora. For example, if we have a small piece of steel and a larger and much heavier piece of aluminum, our senses tell us that the aluminum is heavier and larger, not that it's less dense.
So if I had two pieces of steel, one smaller and one much larger, nothing tells me that they have the same density, only that my senses tell me that one is larger and heavier.
That's correct. So we have to put this in context for our students, and we can do this by working on it mathematically. I think Aurora can help us here.
Density is the mass of an object divided by its volume, or D, equals m over v. Mass is normally measured in grams, while volume is measured in either cubic centimeters if it is a solid or milliliters if it is a liquid. Remember, though, that 1 cubic centimeter is equal to 1 milliliter, and they are therefore interchangeable regardless of the state of matter of the object.
Thank you, Aurora.
So Professor Schnaus, can students only use this equation for density?
Well, actually, Captain, like all equations in math, we can solve for one variable if we know the other two.
In math, this is called equation manipulation, which means you can rearrange an equation so that the unknown you are trying to calculate is on its own on one side of the equation. As it relates to density, you can use the equation three ways. You can solve for density by dividing the mass by the volume. You can solve for volume by dividing the mass by the density. You can solve for mass by multiplying the density by the volume.
Very good, Aurora. Why don't we demonstrate this for our students? Here we have a cube and a scale. So we can calculate the mass of the cube by placing it on the scale, and we get 2.34 grams. We can then calculate the volume using our formula length times width times height. We can then take our ruler and measure one side, which is 4.5 centimeters. And since this is a perfect cube, we know that all sides are equal. We would multiply 4.5 times 4.5 times 4.5, which gives us a volume of 91.13 centimeters cubed.
So the density of this object is 2.34 grams divided by 91.3 cubic centimeters, or 0.023 grams per cubic centimeter?
Very good, Captain.
But what if we have an irregular object that we can't readily measure the length, the width, or the height?
No problem. Remember when we mentioned earlier that we can measure volume in cubic centimeters or milliliters?
Yes.
Well, we can take, with irregular solids, we can use a water displacement method.
The displacement method can be used to accurately measure the volume of oddly shaped solid objects by measuring the volume of fluid displaced when the object is submerged in water. When the object is completely submerged in water, the amount of water displaced in milliliters is equal to the volume of the object. This is known as the Archimedes principle.
And here we have an irregular object. If we take this irregular object and place it in a graduated cylinder that we filled with water and dyed blue so that we can see it, we see that we start with a given amount. Once we add our object, the water displaces or rises up by a given amount. So if we take that final number minus the initial number, we're going to get a volume, which would be 0.5 milliliters.
That's amazing. And now that we've reviewed the mathematical side of density, what's next?
Well, now we have to define density, and I think Aurora can help us here.
Processing. Density is the measure of the compactness of a material. It refers to how close the atoms or molecules are to each other. Density means more than just heaviness, but includes how much space an object takes up. All substances have density, including liquids, solids, and gases.
What exactly does Aurora mean by compactness?
Well, compactness is referring to how much material or molecules are in a given area. So we can understand this by looking at some everyday circumstances. Right, Aurora?
Yes, Professor Schnaus. For example, if there are too many trees in a forest and they are close to each other, then we say that the forest is dense. Similarly, a car parking lot can be dense or less dense depending on the number of cars being parked there. In both these examples, we relate the term density to how close objects are to each other.
Very good, Aurora. Perhaps you could show us using the hologram emitter the difference between two objects and their relative densities so we can better understand compactness.
I would be happy to. In this example, we see two objects. One is made of steel and the other is made of aluminum. Although both objects are the same size, the one on the student's left has more space between its atoms as opposed to the one on the student's right. Therefore, the one on the left is less dense than the one on the right.
Wow, that really helped me understand the differences between compactness of objects. Thanks, Aurora.
You are more than welcome, Captain Codwell. I like using my hologram e-meter to help children learn.
And now that we understand compactness, I think we need to move on to density as it relates to solids, liquids, and gases. Right, Aurora?
Of course, Professor Schnauz. Which would you like to start with?
Don't you think we should start with solids, since that's probably the most familiar objects that students will be encountering?
I agree. Aurora, let's start with density of solids.
Various rocks, woods, metals have a characteristic density specific to that substance. The density of objects can be found by either calculating it using the density equation, or it can be found in various scientific reference materials. For example, the density for a specific element can be found on the periodic table.
Well, that's simple, but what about liquids? I'm sure they have different densities too.
Correct. Let's start off by looking at two common examples, and let's look at our first one, which is going to be water, which is the standard that we use to compare densities of all liquids on Earth.
Processing. Pure water has a density of 1 gram per cubic centimeter. For this reason, it is used as a standard because its density of 1 is easy for scientists and laypersons to remember, and water is a very common and plentiful compound on the Earth.
Correct. Now, have you ever tried mixing oil and water? You would see that the oil floats above the water when we try to mix them. This happens because the density of water is higher than that of oil.
The density of oil is 0.93 grams per cubic centimeter, which is less than that of water, which is 1 gram per cubic centimeter. Since oil does not dissolve in water, it stays separated from it. Incidentally, this is what makes cleanups possible after large oil spills in seawater. Because the oil floats, the oil is scraped or skimmed off the ocean surface. Another such example can be seen in salad dressing, where oil and vinegar do not mix, as vinegar is denser than oil.
What about liquids that are denser than water?
I'm glad you asked. Here we have a liquid. This is colored corn syrup, which is denser than water at 1.4 grams per milliliter. As you can see, when we add the water, it stays on top because it's less dense than the syrup.
That sure is something. But what about ice? That's a solid. But it floats on water?
Processing. Ice is less dense than water because when water freezes, it expands. That same mass of water now takes up more space because the water molecules are further apart. The frozen water is now less dense than water in its liquid state, and so it floats. An example of this is icebergs of frozen water in the ocean, or the thin layer of ice covering lakes and ponds in the winter, with the ice on top and the unfrozen water underneath.
How interesting. But how does density relate to gases?
Well, just like water is our standard for evaluating liquids, air is our standard for evaluating gases and follows the same principles of density. Right, Aurora?
The density of air is 0.00125 grams per cubic centimeter. If you have ever been to a carnival or special event, you may have seen people selling balloons that float in the air. The balloon that floats in the air is filled with a gas called helium. helium gas is less dense than the air around it. The density of helium is 0.00018 grams per cubic centimeter. It is this difference in the density of helium gas as compared to the air around it that makes it float in the air.
And here I have two balloons. This balloon contains helium, and it floats because it's less dense than the air around it, just like Aurora said. This balloon does not float because it contains sulfur hexafluoride.
Sulfur hexafluoride is an inert, non-toxic, colorless, odorless gas. It is used in electrical circuit interrupters, electric piping, and as a gaseous insulator. It is one of the heaviest known gases with a density of 2.863 grams per cubic centimeter.
Correct. And the reason it doesn't float is because the gas in it is more dense than the air around it.
That's amazing. I can see how density applies to gases, similar to solids and liquids. And I think your students have a better understanding of the concept of density now. I'm just wondering how this applies to planetary geology.
Well, in terms of the 8 planets of our solar system, they vary greatly, not only in terms of size and mass, but also in terms of density. Right, Aurora?
The 4 inner planets, those that are closest to the Sun, are all terrestrial planets, meaning they are composed primarily of silicate rocks or metals and have a solid surface. On these planets, density varies the farther one ventures from the surface towards the core. The 4 outer planets are designated as gas giants or ice giants and are composed primarily of hydrogen, helium, and water existing in various physical states. While these planets are greater in size and mass, their overall density is much lower. In addition, their density varies considerably between the outer and inner layers, ranging from a liquid state to materials so dense that they become solid ice.
Correct, Aurora. Density plays a vital role in understanding a planet's surface gravity, and it also helps us understand how a planet formed.
Correct, Professor Schnauz. Scientists theorize that after the formation of the Sun at the center of our solar system, the planets were formed from a circular rotating disk of dense gas and dust left over from the newly formed star also known as our Sun. The 4 inner terrestrial planets resulted from the denser dust grains in the inner solar system, while the 4 planets in the outer solar system were formed from the less dense gases that were left over.
Well, I can see why density is so important to so many fields of science.
I think that's all the time we have for our students today. I think we've learned a lot about density, and thank you, Captain Caldwell, for joining us.
I don't know who learned more, me or the students.
Aurora, please terminate our transmission to Earth.
Transmission terminated.
So, Captain Caldwell, how did the lesson on density go today with Professor Schnauz?
I learned a lot about density, solids, liquids, and gases. I also learned how density played a part in the formation of our solar system.
You know, I've always thought that scientists who study planetary geology are the real rock stars of science.
Oh, that was pretty bad. I mean, real bad.
Processing. A rock star is a famous singer or performer of rock music or a person treated as a celebrity, especially inspiring fanatical admiration. Specialist Barber, I am confused. I do not see how this term would relate to the science of geology.
No, Aurora, I was making a joke. The humor comes from the fact that the word rock is in rock star and that geologists study rocks.
How interesting. Processing. You know, Specialist Barber, you should never expect perfection from geologists. After all, they all have their faults.
Was that a joke?
You know, Specialist Barber, there is no halfway with a geologist. It is all or nothing?
You know, I'm not sure, but I think it was.
Why is it hard for a rock to be a diamond, Specialist Barber? It's because of the pressure.
Wow, these jokes are not getting any better.
What did the stone say when it ended up at the bottom of the hill? That's how I roll.
And on that note, I think we should say goodbye, Aurora.
Goodbye, Aurora.
That is not what I meant. Forget it.
This concludes our latest episode of Spacegate Station. Please join us on our continuing adventures as the crew of Spacegate Station provides engaging enrichment or remediation-based instruction to improve your understanding of science, technology, engineering, and mathematics, terminating communication with Earth